Functions, 4-1. A function is a type of relation, and a relation is any set of ordered pairs. Relations map domains onto ranges. The domain is what goes in, and the range is what comes out. Here's the formal definition of a function. A function is a relation in which every element of the domain is mapped to exactly one element of the range. Keep this definition in mind when we look for the different tests of a function. And so let's look at a series of functions. Are these relations functions? Here's a mapping. Is this a function or not? Yes or no? Think about it. The answer is yes. It is a function. Every element of the domain is mapped to exactly one element in the range. Here's the domain, and here's the range. Okay, next one. Is this a function? Yes or no? The answer is yes. This is legal. Every element of the domain is mapped to exactly one element in the range. This overlap on the range is okay. As long as you're well defining where each element of the domain is going to, it is a function. How about this? Is this a function? No. Because 1 is being mapped onto both the kitty cat and to Julius Caesar. Okay? See, the splitting off there makes this not a function. This is okay, 1 and 2 both going to Julius Caesar. But no, 1 heading off to 2 different things means that you don't have a well-defined function. Let's look at these visually now. It's a collection of objects here, and we see that we've got several points that are all mapped onto 3. Is this a function? Yes. This is a function. It's okay to map onto these things. You can have several points on the same horizontal line, as long as each x is going to one specific y. How about here? Is this a function? No. It flunks what we call the vertical line test. We can make a vertical line here that passes through 2 of the points on the function, and therefore it flunks the vertical line test. Flunks the vertical line test. If any vertical line crosses the function more than once, then it is not a function. Let's look at our next one. This is something called the greatest integer function. Y equals brackets of x. So for instance, if you have the greatest integer of 3.2, that gets turned into 3. Greatest integer of 3.9 also gets turned into 3. So it's not a rounding function, it's a truncating function. Careful with greatest integer like negative 1.5. That actually goes to the greatest integer to the left of negative 1.5, which is negative 2. See how negative 1.5 is going down to negative 2. It's also called the stair-step function. You can do it on your 89 with int of x. You should practice working this on your 89. Now notice how this is still a function. Its domain is actually all reals. Its range is just the integers, because you're always given the greatest integer as the output. And it conveniently passes the vertical line test. See, at a point like 4 here, that's why I have to put a closed circle here at 4, 4, and an open circle at 4, 3, so that we're not sending 4 to 2 different points. As soon as you get to 4, it makes a sudden jump up to 4. Now, this is a piecewise defined function, defined in 2 parts. X squared plus 1 for x less than or equal to 1, 2 minus x for x greater than 1. And you can do this on your T89 with these commands. Notice this big vertical bar, that's the width symbol, that's to the left of the 7. And you can use it to put conditions on your calculator. Notice you got the greater than less than on your calculator right in the front space there, but to get the equals, you have to hit the diamond key, and then the greater than or the less than to get it to be greater than or less than equal to. What does this look like? Here we go. It's part of a parabola and it's part of a line. It's a parabola when x is less than or equal to 1. It's a line when x is strictly greater than 1. Notice how 1 will go to this rule, go up to 2. We put an open circle at 1, 1 to show the beginning of this next section, making this discontinuous right here. Also, I've shown you that this is how you do it with GeoGebra. It's actually backwards. You don't use a with statement. You put an if conditional statement on. If x is less than or equal to 1, comma, then put that function down. If x is greater than 1, comma, 2 minus x. Okay? I think you can also do it in one statement with an if, then, else, with a third comma. You can explore that. So let's review some of the tests we did for functions. A vertical line test, if any vertical line crosses the relation more than once, then it is not a function. Or you can say it in the positive sense. If all vertical lines cross the relation only once or not at all, then it is a function. Mapping test, if any element of the domain is mapped to more than one element in the range, then it is not a function. That goes against the definition we talked about. Each element of the domain should only go to one element in the range. In the orders pairs test, if any two ordered pairs have the same x but different y's, that is not a function. Notice if you have the same x and two different y's, you're on the same vertical line, hence the vertical line test. Just a little interlude here. Where is this map of the U.S.? It is somewhere in a park in the city of Milwaukee, only 0.2853 miles from Chipotle. Now, let's take a look at operations on functions. We're going to first do these algebraically and look at what these mean visually. First, algebraically, let's do up some of these. F of x plus g of x, that's just 1 minus x squared plus 2 minus x, so I combine it into 3 minus x squared minus x. F of x minus g of x, 1 minus x squared, make sure you subtract off the whole entire quantity, 2 minus x. So you get 1 minus x squared minus 2 plus x, or negative x squared plus x minus 1. F of x times g of x, so that's going to be 1 minus x squared times 2 minus x. So we can FOIL that out as first outer inner is minus 2x squared, last is plus x cubed. So we get x cubed minus 2x squared minus x minus 2. And finally, division. F of x over g of x, 1 minus x squared divided by g minus x. So just stop leaving that whole. Can't be reduced. 1 minus x squared is minus 1 minus x times 1 plus x. Now, composition of functions is a little different. You also notice that sometimes a composition is written this way. F open circle g of x means f of g of x. And g open circle f of x. So sometimes you might see written with that little open circle symbol for the composition. It's not the same thing as multiplication. To do f of g of x, replace the g of x with 2 minus x, and the output of the g function becomes the input for the f function. So it becomes 1 minus 2 minus x quantity squared. And we traditionally expand this out. 4 minus 4x plus x squared. We subtract each part, 1 minus 4 plus 4x minus x squared. So you get negative x squared plus 4x minus 3. Now notice, when we do the composition in the other direction, it's g of f of x, is 1 minus x squared. And I would put that into the g function. The g function is 2 minus something, so it's 2 minus the quantity 1 minus x squared. So you get 2 minus 1 plus x squared, or x squared plus 1. Notice the composition done in different directions doesn't yield the same thing. Now let's look at these visually. Let's see this is all of them all at once. Let's look at them one at a time on GeoGebra. We're on GeoGebra, and we can look at just one of these functions at a time. Let's first of all look at the addition, h of x. Notice how h of x is taking all the y values, and for the same x, adding up the two y coordinates. So here on the red function, it's 1, and in the green function, it's 2. 1 and 2 is 3 on the purple function. Notice where the green function was 0, it doesn't change the red function also. The probe function crosses there. Also is going to happen over here when the red function is 0. Notice the green function agrees with the purple function. All right, that's addition. Now we can look at subtraction, being the difference. So when we take 1 minus 2, we get negative 1. Notice this is never 0 because this function is always below the other one. So when we take the red function minus the green function, it's going to end up being a negative value. And let's look at the multiplication of the two. Notice we end up with a cubic. And notice where the cubic has its zeros. It has its zeros where each of the different product functions had their zeros. That's one reason why we would take polynomials and factor them to find their roots. Finally, we have the division. And very strange here. And you might wonder, where's the rest of it? Over here, we end up with a hyperbola. With x equals 2 is where you get division by 0, so that's undefined. So you got to be careful just with the division of functions. If the bottom function is 0, it's going to create an undefined part, and that's not part of the domain of the composition of the two functions anymore. Now, composing functions. Here's our 1 minus, this is our f of g of x. F of g of x. And notice with f of g of x, the domain of g of x, the inner function, is all reals. And the output is all reals because it's a line. But then when you put that inside the f function, which can take all reals, but it only outputs things 1 and under, notice the composition then ended up with a range of 1 or less. Now we go in the other direction. Something different happens. Ends up going like that, being 1 or more. Now let's see why. Why does this function have a domain of all reals and a range of y greater than or equal to 1? Well, the inner function now is 1 minus x squared, which can take all reals in, but then only puts out things 1 or less. So when you're at 1 or less going into this line, 1 or less going into the line, notice your y values are going to be 1 and above. So that's why the composition works that way. Okay. That's composition of functions. And we're all set. Flange out.